In this example, the mechanism for the reaction of the hydrolysis of carbonate esters was investigated under two different types of conditions. In path A, the reaction was carried out under basic conditions, using hydroxide as the base, and in path B, the reaction was carried out in the presence of a catalytic antibody. And so in both cases, the same starting material was utilized, and that starting material was measured. The rate constant for the disappearance of the starting material was measured as a function of time with different substituents. In the first case, path A, a Hammett plot was developed, and the rho value for that Hammett plot was moderate, and it equaled 2.7. It had a positive slope, and so this tells us that negative charge is developed in the transition state. And that when we have electron withdrawing substituents, the rate constant is enhanced. And so this is consistent with path A, where in the first step of the reaction, we end up with a negative charge on the nitrogen through the deprotonation of the amide with hydroxide, and then the rate determining step of the reaction is the collapse of the anion to release phenolate. And in that rate determining step, negative charge is developed onto the phenolate ion, which can be removed with electron withdrawing substituents. And so this is consistent with the moderate rho value of 2.7. However, surprisingly, when the reaction was carried out in the presence of a catalytic antibody, and the rate constants for the reaction were again measured as a function of substituent, and the rho value was determined through the Hammett plot. In this case, the rho value equaled only 5.26. So this is a very shallow slope. And this would indicate that the mechanism in the presence of the catalytic antibody is different than the mechanism under hydroxide conditions. And so we can think about the fact that when we add the catalytic antibody, now this substituent is having little influence on the rate constant for the reaction. And so we need to think about another mechanism that might be consistent with the Hammett plot result. And so this is shown in path B, where instead of hydroxide acting as a base in the first step of the reaction, in this case hydroxide acts as a nucleophile, and it reacts with the electrophilic center of the carbonyl to give us a tetrahedral intermediate. And it's at this step where the tetrahedral intermediate now collapses and kicks out our phenolate ion. And so in each case, phenolate ion is the leaving group, but in path B, the rate determining step is the step prior to the loss of the phenolate ion, which is connected to the substituents. And that first step has little charge change upon going from the starting material to the initially formed tetrahedral intermediate. And this is consistent with the rho value being small and the influence of the substituent being almost negligible. Okay, so let's look at the mechanisms for the two different pathways, reaction pathways of the carbonate esters in a little bit more detail. So in path A, under hydroxide conditions, the hydroxide acts as a base in the first step to remove the proton on the nitrogen to give us an amide, which then undergoes a collapse to generate the transition state structure as drawn here. And you can see that in this transition state structure, we start to develop negative charge on the oxygen to generate the phenolate. And so this negative charge development is in communication with our substituents, and this is consistent with the rho value, which is positive, of 2.63. So the rho value that we obtained under conditions where a catalytic antibody was contained in the solution was much smaller at 0.53. It was still positive. And so this suggests that a different mechanism must be taking place when the catalytic antibody is present in solution. And so another mechanism that you could envision is, in this case, the rate determining step is the first step of the reaction. And this is consistent with the transition state structure that's shown here, where we still have a developing negative charge, but now it's on the oxygen of the tetrahedral intermediate, and so it is no longer in direct communication with the substituents. So this results in a much reduced influence of the substituents on the rate constant for the reaction, and this is consistent with a more shallow slope for our rho value of 0.53. So this is a really nice example that tries to explain that you can use rho values and their slope and also their magnitude to give information on mechanistic detail of the reaction that you're looking at. These two rho values for the hydrolysis of the carbonate esters are significantly different, and so this indicates the same mechanism must not be taking place under the two different conditions of the experiments.